lot for all the organizers for the opportunity to speak and for bringing us together here. And also thanks a lot, Axel, for setting the stage now that I don't need to feel like the first physicist speaking here. So the goal of this talk is to report on a recent work where we constructed polylogarithm functions in higher-genus Riemann surfaces, mostly based on a paper that appeared last summer in collaboration with Eric Doker and with Martin Gilling. And also, if I have time at the end of the talk, I will try to outline what's currently in progress. Two separate projects, one in collaboration with Eric and the other one together with Eric and with Benjamin Enriquez and with Federico, who was right there in the audience and who we were yesterday. Yeah, and I think nothing of what I could be telling you today would be possible without the genus 1 prototype of this construction. So we are, in a nutshell, generalizing the elliptic polylogarithms a la Brown-Levin to arbitrary genus. And we are definitely not the first one to present a line of attack to higher genus. There are earlier papers who present connections, like a main tool that I will explain, who explain connections before us, how to attack higher genus polylogarithms. One in work by Enriquez, and another one in a joint paper of Federico and Benjamin. And I hope I can clarify at the end in which way this talk has parallels and differences as compared to those papers. Yeah, and fortunately, you've already seen a talk by Axel where you got a flavor of a string theorist approach. So I have a similar background like Axel. As you heard, in string perturbation theory, people start by drawing Riemann surfaces, which have information about certain gravitational interactions within a string theory. And these cartoons of Riemann surfaces, they usually represent mathematically precise expressions. And they contain a lot of conformal field theory, or more precisely, Green's functions of free bosons and free fermions and Riemann surfaces. And yeah, these Green's functions and conformal field theories have a lot of inspiration, or at least for the main objects that I will present in this talk. It was extremely valuable to have a Riemann surface and a conformal field theory to ask for some suggestions. So this is where some of the inspiration also comes from. Yeah, now, as to broader motivation, if you are not a string theorist, so why bother about polylogarithms, you see in the title. So let's say the most ambitious way of phrasing the long-term goal of this research program is to overcome a trauma from high school, where we learned that integration is harder than differentiation. I think this will remain true, that integrating is harder than differentiating, but perhaps with the joint effort of everybody here, we can at least mitigate this asymmetry a little bit and make sure that we are crying a bit less when being asked to integrate a large bunch of functions. Okay, so the modest step where I hope that this paper has something to contribute to is to give ingredients to construct a good function space, or a well-adapted one, which is, first and foremost, closed under integration. So we are not yet there, but at least it's a proposal that these polylogarithms may be used to design such a function space, closing under integration. And this is usually done geometry by geometry. You start with rational functions. There you're on the sphere. And since rational functions by themselves don't close under integration, you need the logarithm and later the polylogarithms. So I guess we saw yesterday that this is the consensus notation for multiple polylogarithms, like iterated integrals on the Riemann sphere. And to really talk about the function space that closes, we need to multiply them by rational functions, or here they are representative through a D-log form. Okay, so the hope is that we can write down a similar function space for Riemann surfaces of arbitrary genus. And needless to say that the next question after that is to deal with higher dimensional varieties. So there's so much to do far after that. Okay, and let's not attack this with a nuclear bomb principle. Let's construct a function space which is not too large, which is still small enough that we can somewhat control the properties. So maybe one can phrase the more ambitious goal of being minimal, but at least not too large.
So what is exactly the nuclear bomb?
completely exhaustive in trying to write down a function space, like having redundancies. What annoys is if you can't decide whether expression A equals expression B. So let's make the function space small enough that it's still a feasible task to classify all relations. Okay, so this is the kind of philosophy behind this talk. And now let me be a bit more concrete about the tools. So I will spend most of the time constructing a connection, a flat connection J, which is a one form in a marked point X on the Riemann surface. So depending on the setting, it will not only depend on one marked point, but typically on more marked points and moduli of the Riemann surfaces, like modular parameter tau in the case of Axel. And once we have a flat connection, once we have a solution to this flatness condition here, then we can almost claim victory. Then we can generate an infinite series of iterated integrals that are homotopy-invariant, that only depend on the endpoint of the respective path, as long as you don't pass it along poles. So then, by virtue of homotopy invariance, you can really sell that iterated integral as a function of the endpoints and not as a function of all the details of the path. Yeah, so the notation throughout this talk is that the path-ordered exponential is expanded out in this way, following physicist convention where latest variables are on the left, such that a z derivative pulls the connection J to the left.
You don't have factorials.
Oh yeah, so since this is a simplex rather than a square, so there's a hidden a half, given that the simplex has half the volume as compared to the square. It's just a solution to an ordinary differential equation in X. Okay, so for this reason, I will spend most of the time talking about connections, and the formula involving polylogarithms will be more in a minority.
So what exactly is supposedly homotopy invariant here?
Oh yeah, every iterated integral that pops out from here, as I will tell you, there will be certain Lie algebra generators in this flat connection. So we have, among other things, a power series and non-commutative variables, to be called A and B in the genus 1 case. And then each coefficient for arbitrary words in A's and B's will be by themselves homotopy invariant iterated integrals. Okay, so the structure of the talk is to now focus on genus 1. I'll try to give you a lightning review of selected aspects in the work of Brown and Levin. And then I will show the proposal how to generalize this to arbitrary genus, and I hope there will be enough time to talk about work in progress.
Put the blackboard up.
Oh, yes. This one down?
No, this one up. This one up.
This one up.
This one
up. Ah, okay, thank you. Yes.
Yes, I've seen.
Next time with more energy. Sorry about that. Okay, so here's a lightning review of the elliptic polylogarithms a la Brown and Levin, with acronym BL to be used throughout the talk. And as you can see, I've here specified my favorite parametrization of the torus. So this will be about the genus 1 case. We parameterize the torus in the same way as Axel did in his talk. Take the A cycle to be going from 0 to 1, the unit interval, and then the B cycle going from 0 to some complex number tau in the upper half plane. So the torus is then the interior of this parallelogram. And my conventions for the Jacobi theta 1 function that will appear here and there is probably same convention as Axel used. Okay, so which flat connection did Brown and Levin use to construct the polylogarithms? Here's another attempt to make the prototype connection and the flatness condition visible. So the J of interest here start by writing down the schematic formula and then go ahead filling in the details. So it depends on 1 mark point of the torus, or you can even say that it secretly depends on 2 mark points. Read it as a difference, x minus 0, with a second mark point fixed at the origin. And so here it will involve generators, well, 2 generators that form a freely generated Lie algebra. It's called an A and B, both non-commutative and no relations whatsoever among their nested brackets. And there's first of all some B appearing here. And now comes the other generator A with many, many B's. And here's a function omega, which did appear in Axel's talk, but I will define it in more detail in the next blackboard. Okay, and before even going into what's inside this omega, let me stress that this is supposed to be a connection that lives on the torus and therefore respects the periodicities here, periodic under A cycle and B cycle shift. So whatever this function omega may be, it should better obey these double periodicity properties. So it's really a connection that lives on the torus. Okay, now let's get a little bit closer to this doubly periodic object omega here. So this is, as you heard it from Axel, the Kronecker-Eisenstein series. And for practical purposes, let's expand it in the non-commutative variables A and B. So it's view it as a power series in ad B, Taylor series in the adjoint action with respect to that letter B. And term by term in this expansion, we will see that the general formula for omega defines certain integration kernels, F1, F2, which are individually doubly periodic, and that, frankly, strict theorists had really a lot of fun with in order to nicely represent certain conformal field theory correlators, how to simplify expressions formed from Green's functions of free bosons and free fermions. Okay, there's admittedly an infinite power series, so this is a never-ending expansion with arbitrarily high powers of B, but at the very least, this infinity of terms is regular as x goes to the origin. Or conversely, by analogy with genus 0, where we needed simple poles in our integration kernels, there is a simple pole right here. Simple pole at the origin, and certainly also at all of its translates under the A cycle and the D cycle. Okay, next step is to give you the detailed definition of this Kronecker-Eisenstein series. Sorry to those who know this object already by heart. That's a good moment to check your emails. Okay. Not really. So there's an explicit form of that gadget up there. So first of all, omega itself is what I refer to as the series. And now these expansion coefficients, Fn, I will refer to as the kernels. And one of the main results is a generalization of these kernels to arbitrary genus. Okay, so while you saw an AB in one of the arguments of omega, I will just write more innocently alpha for that second argument, where you may or may not want to plug in an AB. And okay, to start with, we want a sensible generalization of a KZ connection at genus 0. There were these D-log integration kernels that are now wiped out. And the simplest way of realizing a simple pole on a genus 1 curve is to put a theta1 function with this variable x downstairs. But now this x dependence has to be handled with care. As you know, theta1 is quasi-periodic, and to mitigate that, let's also put something compensating here in the numerator. Of course, not in a way that we cancel, but yeah, maybe this is a defensive way of introducing a simple pole while keeping the monodromies under the B cycle multiplicative rather than additive. Okay, so this is maybe a 0th order approximation for the connection of choice, but it's not yet doubly periodic. So by quasi-periodicity of the theta1, there are still some unpleasant monodromies along the B cycle. And to get rid of those, one goes very far and sacrifices meromorphicity. Yeah, I mean, this is an old story. The quest for elliptic functions often comes at the cost of meromorphicity, unless you are willing to tolerate double poles or additional auxiliary points. So here the path chosen is no double pole, please, no auxiliary point, please. So therefore, the only way out is to accept this mild non-holomorphicity through the x bars up here. Okay, now it's this object which is supposed to get expanded in order to read off the coefficients of a's and b's in the connection. So the task is to expand in the second argument, which starts with a simple pole. There's after all an 1 over alpha here. And then there is an infinite number of non-singular terms in this alpha expansion. And the coefficient of this nth order in alpha is here given the name Fn. So these are the doubly periodic integration kernels to be used in the Brown-Levin connection. They are doubly periodic because the series is for arbitrary alpha doubly periodic. So needless to say that this propagates to each order in this Laurent expansion. Okay, so a concrete example is the singular fellow F1, which I already highlighted. So this you can verify from the theta functions to be the d log of theta1. This is not yet periodic under B cycle shifts, but fortunately the exponential will help about that. So here this is the doubly periodic completion. And yeah, from the d log theta1, you get to the promised simple pole and infinite series in regular terms, which in one case even involve an x bar. Okay, so this is how to think about these f's and how to make sense order by order of the expansion of the Brown-Levin connection in the non-commutative generators A and B. And yeah, the goal was to obtain a flat connection. So this step will hopefully make sense of the additional ingredients, which you see up there in the equation for J Brown-Levin. So flatness here is non-trivial. One part of the flatness condition will detect, there is some anti-meromorphicity here. So J is not closed under this, but you need the help of the other term in the flatness condition. And it turns out that the right-hand side does the job and saves flatness, which at the end of the day can be traced back to the differential equation of this Kronecker-Eisenstein series, which you can verify in real time for yourself. I mean, the only x bar dependence is in the exponential. So therefore, the anti-holomorphic derivative looks like that, which is just 2 lines of algebra away from verifying the flatness. Okay, so by this flatness condition, we can be sure that taking iterated integrals of JBL gives actually homotopy-invariant such iterated integrals. So now it's time to harvest and get actually infinities of homotopy-invariant iterated integrals by sticking that JBL into a path-ordered exponential. Okay, so the convention you have seen before. This is to be read as 1 plus the thing in the exponent for length 1 integrals. But then there are also quadratic terms in JVL with an integration simplex, and so on and so forth, arbitrary powers of JVL. And well, JVL is algebra valued involving A's and B's. It strictly speaking contains words of arbitrary length, but okay, maybe this is not so impressive since also the path-ordered exponential goes to arbitrarily many powers of JVL. So for sure you can expand this in words in A's and B's. And now the coefficients in these words in A's and B's are called elliptic polylogarithms. And they are guaranteed to be homotopy-invariant because the entire generating series is. And of course, you need to pay attention to the fact that the A's and B's don't commute. So this is just one example to give you a flavor of. And note that it's a non-trivial bookkeeping task to assemble this AB elliptic polylog, because you could take the AB from a single power of JVL. If it all comes from a single JVL, then you grab a F1 function, since F1 goes with the bracket B, A. But you also have an admixture of quadratic in JVL, taking A from the first JVL and B from the second JVL.
So you have a question to F1. Why do you call kernel? Why do you say kernel? You said in kernel F1 in the first line.
Yeah, so maybe this is a bit of physicist jargon. The elliptic polylogarithms are iterated integrals, mostly of the f's, and of course of this pi over in tau term. So it's something that appears constantly inside an integrand, hence I call it integration kernel. No deep meaning. Let's say it's mostly jargon to call it integration kernel. Okay, and yeah, as I just said, 2 contributions to this, and you really need to complete all of them to see homotopy invariance. I mean, don't be disappointed if individual terms are not integrable. You really need to go through the complete bookkeeping if you want to try this at home.
So, can you say a word about dx, please?
Oh, sure. So before I was saying this is a power series in...
Oh, I'm sorry.
He was right there.
No, right.
Okay. Yeah, but maybe I give you the most general definition of these polylogarithms, which is sum over all words in A's and B's.
Formally expanding.
Previously, I thought it was.
For each word W in A's and B's, there is a Brown-Levin polylogarithm, and yeah, so you can label them by words in 2 letters A and B. And so later we will do the same at higher-genus, but with several A's and with several B's. Okay, yeah, since JVL is not meromorphic, clearly also the polylogarithms are not meromorphic. And if you don't like that, you can perform non-Abelian gauge transformations. So for instance, there is a formulation of elliptic polylogarithms, which was very successfully used in particle physics, denoted by gamma twiddle for the connoisseurs. And they can be obtained by a simple non-Abelian gauge transformation of this path-ordered exponential. Yeah, they were introduced in the work of Johannes and Claude and many others in the room. Okay, I think many physicists to talk to about the prominent use of elliptic polylogarithms in particle physics. And similarly, they really made life significantly easier in string perturbation theory. Yeah, so at the moment we saw a couple of kernels, Fn, getting introduced. And here I chose a path through theta functions, which is still a smooth sail at genus 1, where the complexity of theta functions is relatively manageable. But for the higher genus version of all that, I won't have a theta function description to offer, at least not now. So therefore, I will give a reformulation of the genus 1 story in a way that transition to higher genus is smoother. Okay, so these Fn kernels, they have a double life. they can be peeled out of the Kronecker-Eisenstein series that you saw before. But I will now give you an alternative construction for all of them, which just starts with the bosonic Green's function and certain operations on it. Okay. So I need to give this a push. Yeah, so here is the alternative construction. And as I was saying, it's now the torus-Green's function that will take center stage. So for conformal field theory experts, this is the two-point function of the free boson on the torus. Oh yeah, actually we saw it in Axel's talk. It's exactly this log of theta 1. Absolute value squared to be real analytic. And then to repair the B-cycle monodromies, there's also this anharmonic term here. Okay, here this is the standard torus-Green's function, which was at the heart of the definition of modular graph forms. And let's now see how the ingredients of JBL come from this. And the operations you need are derivatives and convolutions. Maybe not a surprise if you hear Green's functions. It participates in convolutions for its living. But let's first get the singular integration kernel, F1, from the first meromorphic derivative. Well, I shouldn't call it a meromorphic derivative, because this one will still leave some in x over in tau behind. And now all the higher kernels come out from convolutions, in the sense that we do a surface integral over the entire torus. Here is a modular invariant integration measure. And we convolute the derivative of the Green's function into the previous Fn kernel. Let's see, maybe I should call this integration variable z. Okay, so you first generate F1 from derivative, and then F2, F3, and all the higher order friends are coming from here. It's admittedly not manifest that this gives rise to the same objects as the expansion of the theta functions, but yeah, maybe with 2 or 3 pages of algebra you can check that. Good. Almost there to get to higher genus, but perhaps a very last remark on the topic of integrability. So as I said before, the long-term goal is to construct function spaces that close under integration. And already in the Brown-Levin work, there was a discussion of why these elliptic polylogarithms have a closure property under integration over Z. And importantly, you need certain quadratic identities among the Kronecker-Eisenstein series or the kernels Fn, so-called Fay identities. If you're in the configuration space and you plan to do multiple integrals over many marked points, then you can quickly see that you really need an identity of the following type. Suppose you have a product of 2 such omegas at different marked points and also of different bookkeeping variables. Then you can shuffle around the first arguments. And this is as if we were doing partial fraction relations from the D-log kernels at genus 0. And indeed, for all of you who played with genus 0 polylogarithms, you probably remember the moment where you did need to apply a partial fraction relation. And it's exactly the same at genus 1, that sooner or later Fay identities become necessity. And to give an even more tight analogy with these partial fractions, let's look at a bilinear in F1s. Singular kernels with a simple pole at the origin. So certainly this bilinear f1s doesn't appear in the path-ordered exponential above, so you may start to worry if this can still be integrated within the realm of Brown-Levin polylogs. And the answer is that you can, because these Fay identities, if you peel off appropriate powers in alpha 1 and alpha 2, will give you something like that, where at most one instance of the variable x appears that you plan to integrate on one. So in the first line, you can pull this and that factor out of the x integral, and there's something similar in the second line, which does appear in the path-ordered exponential of JBL. Okay. And if you just zoom onto the first line, then you will probably recognize that at the level of the singular terms, this is mimicking the partial fraction relation from genus 0. But this can be written like that. But of course, at genus 1, we need to pay more attention. Having the right poles is not enough. You furthermore need the second line as a meromorphic completion. I mean, the first line cannot be the end of the row, because just hit it with d bar of x, and you will get a contradiction. The second line is meromorphic completion, but doesn't introduce any further poles. Okay, so this is...
Why do you say this is an analog partial fraction?
You just wrote it. It's written. So
if you consider that limit, so say tau goes to infinity.
oh no, under tau to infinity, the f2 becomes a constant. So it's not as simple as checking out the tau to infinity limit. I'm doing a simultaneous series expansion in x minus a and x minus b. But it's exact, because both sides, the difference of the two sides is holomorphic in all variables and integrates to 0. So it must vanish. Okay, this brings me to the end of the genus 1 review, and now I will proceed to higher genus. Is there any further question about genus 1 before we leave that behind? Okay, you can see some preparatory material about higher genus. Above is a cartoon of the Riemann surfaces that I will be interested in. You can already see a choice of homology cycles. If H is the genus of the surface, then you have a total of HA cycles and likewise HB cycles, which are drawn to realize a canonical intersection area. That A cycles don't intersect with A cycles, and likewise the B cycles don't intersect with B cycles, but only the pairs of the ith A cycle and the jth B cycle, only those intersect with a Kronecker delta as an intersection pair. Good. And apart from the homology H1, we should also talk about the cohomology. And out of the 2H dimensional cohomology, we can pick H members to be Abelian differentials. Holomorphic one forms in marked points on that surface. And yeah, throughout, whenever you see a capital letter like I, J, K, L, and so on, you can assume that it's taking values in the range 1, 2, ... all the way to H, the genus of the surface. And you can always pick a basis among these Abelian differentials, such that they are normalized on the A cycles, meaning that the A periods of the omega j's are giving you a Kronecker delta. Okay, so then you have some sort of fixture basis of the omegas, and you no longer have a choice for the B periods. So now you can think of the B periods as describing you the shape of the surface. So these objects, capital omega ij, this is the period matrix. And I'm a bit embarrassed about the clash of notation, capital omega back there has unfortunately nothing to do with the period matrix here. This period matrix. Okay, for small enough genus, the period matrix entries are enough to parameterize the moduli space. And as we know, there is the so-called Schottky inconvenience starting from genus 4, where the entries of period matrices are an overcount for the complex dimension 3g minus 3 of the complex structure moduli. But this won't be an issue for this talk. Okay, some reoccurring combinations will be the imaginary part of omega, which is all over the place. Hence it gets the shorthand y. And even more frequently, you will see the inverse. I'm lazy enough to just write j upstairs when referring to the entries of the matrix in omega inverse. And maybe I'm lying a little bit. You are not seeing this anymore because I'm often hiding the inverse y's in the notation and raise or lower indices. Just ask me whenever something becomes unclear through this index management. So you will see many, many instances of anti-holomorphic Abelian differential, where the upstairs index means that there is secretly a matrix vector multiplication with the inverse of in omega. Okay, what more can I tell you about these Abelian differentials and their interplay with period matrices? It's useful to know about Riemann bilinear, which is a statement about the surface integral. If now we integrate this 1,1 form over the surface with a free index I and j, we can take independent values, then with the above normalization conditions, this is a multiple of Kronecker. And then the last item for that checklist is to introduce the Kähler form. And clearly, there is a H by H array full of volume forms, and one of them is slightly more special, namely when I contract the indices I and j. And here, the convention for this contracted Kähler form is like such. So with the normalization, that contains an inverse H, the genus, to ensure that it integrates to 1 for convenience.
Not Heisenberg H.
Not at all. No H bar. Okay, you can already see there's some Einstein summation convention involved. Like repeated indices are taken to be summed over. So in situations like here, where you see a repeated j, then there is a summation implicit. Okay, so now let's take the next step and talk about a Green's function. So similar to genus 1, the strategy will be to start with a good representative of the bosonic two-point function, and then generate a flat connection just by derivatives and convolutions. So in that regard, the strategy is identical between genus 0 and arbitrary genus, but of course, every now and then there is this extra layer of complexity coming in through the indices on the Abelian differentials. Okay, so now let me introduce the so-called Arakelov Green's function. So one way of defining it is by its functional properties. The Arakelov Green's function is the unique function on two copies of the surface with the following properties. So it's single valued on two copies in the sense that there are two marked points entering, y and x, two marked points on the surface, and it's furthermore taken to be symmetric. I can swap the first and the second argument. And now the key defining properties are it's the inverse to the Laplacian in the sense that this double derivative in x gives you a delta function. But we are on a compact surface, so this by itself is not integrable as a Laplace equation. And the salvation comes from this scalar form kappa defined up there. Okay, so this is identifying the Arakelov Green's function as the inverse to the Laplacian. And I finally need to specify my conventions for the zero mode. So it's taken to be orthogonal to the zero modes with respect to the scalar form, which is a fancy way of saying that it integrates to zero and integrated over the surface against the scalar form. Okay, so this is in principle enough to uniquely fix the Arakelov Green's function. And if you're like me and enjoy having some explicit expressions to get hands on, then you can also go through these formula which define the Arakelov Green's function explicitly. Where, in a nutshell, you start with the prime form. So this is more or less the meromorphic function x minus y plus corrections to make it quasi-periodic on the surface. But it has monodromy, which you need to cancel. So this term here, again an unharmonic one, similar to the one you saw in genus 1, is compensating the immediate b-cycle monodromies. And then there is a second move to subtract the contributions to that integral here. I mean, we are imposing this Arakelov Green's function to integrate to 0, and the first line alone doesn't do the job. And we repair that by brute force. You just subtract out all obstructions of that gadget to integrate to 0. So maybe it's an evenly long debate that we can have with a glass of wine, whether this is explicit or not. But as long as you can control these integrals that are getting subtracted, then you can refer to this as an explicit formula for the Arakelov Green's function. Okay. Then next step is to get a step closer to the flat connection. So let's get straight to the point that with the definition of the Arakelov Green's function, one can work out higher genus counterparts of the Fn kernels from before. And again, the moves are derivative and convolution. Now of the Arakelov Green's function. So let's start with F1, which may have a bit of a surprise. So F1, which was nothing but the derivative of the torus Green's function before, it now uplifts to an rank 2 tensor with h² components. More specifically, F1 becomes such a 2 tensor with indices I and j, again taking values 1, 2, ... h. And first of all, there is indeed a derivative of the Arakelov Green's function. And since the Green's function doesn't have any indices, all I can do is place a Kronecker delta to be on the diagonal here. But if you keep on working with this object alone, you will have some trouble to later get the Laplace equations you want. So already here we need a bit of a tweak. We need to put in something which doesn't have any genus 1 counterpart. So here I'm introducing a traceless tensor phi for you, which firstly showed up in the work of Kawasumi. So here this traceless Kawasumi tensor. In one way or another, you can think of it as describing the breakdown of translation invariance, in the sense that the Green's function depends separately on x and y, and not just on a difference. But okay, here, to proceed in the storyline of the talk, let's just note that it's defined as a convolution. You convolute Arakelov Green's function against the most general volume form. So this is not kappa. Only upon contraction of I and j, this will become a Kerner form kappa. So at genus 1, I couldn't do that. At genus 1, this would be kappa dead on and vanish. But not so at higher genus. As long as you don't trace out I and j, this is non-zero, and hence you get a traceless tensor, denoted by phi and baked into the F1s. Okay, so this is the first step. And now let's go higher. Let's now think about an analog of F2, F3, and so on and so forth. And maybe here the parallel to genus 1 becomes a bit tighter again. Oh, maybe I shouldn't have erased what I just erased. Let me know if you want to have the page of the notes.
Yeah.
Thank you. So how do we get to the higher f's? Now the tensorial version of all these higher f's are defined recursively, the same way as done at genus 1, at least in the second pass through the Kronecker-Eisensteins. It's essentially a convolution of del g, the derivative of the Green's function. Now I need to be careful again, who is integration variable and who is spectator. We integrate over z, and part of the measure is an anti-holomorphic Abelian differential. And now here comes the recursive step. Here we introduce and we insert a lower rank F tensor. So start with F1 here, then this outputs F2, and so on and so forth. It's a recursion in the rank. Now, if you ask tensor with respect to what, if there's time later, I can explain in more detail that they are tensors with respect to the modular group. So there is a modular group SP to H at genus H, which starts out with an interchange of basis or the homology that preserves the intersection pairing. And under such SP to H transformations, you treat them like tensors and you operate with the C omega plus D part on all of these indices separately. So this is to say in a cryptic way, they have good modular behavior. That's, if you ask me, a direct analog of a Jacobi form of index 0 from genus 1. And of course, it reproduces correctly the way how the FNs in genus 1 transforms under SLT. But okay, to stick to the main storyline, we have now encountered a couple of FNs, or generalizations of these FNs. And let's now put them together in a generating function to eventually arrive at a flat connection. So this is the moment to introduce the analog of the free Lie algebra generators. You were seeing before a single little a, a single little b for genus 1, the algebra of the fundamental group of the one-punctual torus. And now there are more of these a's and b's. So we need one a per a cycle, one b per b cycle. Like that. For the moment, you will only see the b's, but the little a's enter the stage one blackboard later. So for the moment, let's put together all of these f's. And of course, you can view the Abelian differentials as an honorary member in the F family, some sort of F0. So that's why I'm starting with them. And then there are some adjoint actions of the B generator contracted into the Fij above. So it's strictly speaking an operator valued generating series, but you will see in a second what it acts on. Okay, so this is an infinite series which extends the pattern in a, I hope, obvious way. But be careful to put the indices or the b's into correct order. Because on the one side, the b's don't commute with one another. And at the same time, the F tensors are not symmetric under moving around the upstairs indices. So be careful that you respect the order. Okay, so now to check whether this is good or bad for a flat connection, let's test its anti-holomorphic derivatives. And I emphasized before that the Arakelov Green's function is sort of defined by its Laplace equation. And if you chase the Laplace equation of D through all the definitions of the F tensor, then you can work out what the entire generating series does. So that one will just get contracted into bk to the same generating series. Okay, I'm a bit sloppy and I discard the delta distributions, but just keep the points away from one another to be on the safe side. And yeah, so this psi is almost the analog of the Kronecker-Eisenstein series from genus 1. So a comment on the h=1 specialization. In this case, there's just a single component. So j is necessarily set to be 1. And then in the h=1 case, this is almost the doubly periodic Kronecker-Eisenstein. Oh, sorry, it's not the period matrix. But of course there is an at B up front because we don't have any poles. It would in fact be pretty dodgy if I were to try a simple pole in RBI. Okay, so this is the backbone of the Brown-Levin connection, which is correctly reproduced by this generating series psi. And let me now give you the completion to be a flat connection. And yeah, this anti-holomorphic differential equation here is the biggest part of the work to check the flatness. By the way, how am I in time? Well, in terms of minutes, when should I approximate? Well, thank you. Okay. Yeah, let me know when you need to catch the bus. Okay, so now this is the moment to bring the full freely generated Lie algebra into play. Now this will amount to an expression in two H generators, several A's and several B's, so with the usual range of indices going from 1 to H. And here is the genus-dependent flat connection, JH. So again, the prototype is the Brown-Levin connection, which starts out with some dx bar term and a letter B. And this generalizes maybe in the most crude way. And now comes the part that contains the higher genus F kernel. So here is the generating function psi from the previous board, which is a series in ABs. And this in the first place acts on the A's, such that among other things you get the omega i's contracted in the A i's, which resonates pretty well with the zeroth order terms in Brown-Levin connection. And here is a contribution that is perhaps less obvious as generalization. So in order to make sure that in J wedge J you don't get into trouble with this term, yeah, you need to dial a little bit to get also this additional contribution here correct. But yeah, you have my word. This is an essential part to reproduce correctly at H=1, the contribution in Brown-Levin that went like this. And then to see that it requires also an infinite series in ADB, you need to go through the flatness condition. Namely, so this is reproducing correctly Brown-Levin if you specialize the genus 1. And at arbitrary h, it gives rise to a flat connection, which you can check from the anti-holomorphic derivative in the previous form, in the sense that, yeah, once more, this one works out. Okay, so this completes the construction of a flat connection. And now you can again switch to iterated integral mode and plug that thing into the path-ordered exponential to generate a series in homotopy-invariant iterated integrals. And this is what we refer to as the higher-genus polylogarithms from the types. So this is probably not containing any surprises. So by flatness of the connection, the following power series is homotopy invariant. So once more, the path-ordered exponential, integrating to some reference point z. Now I can't take the origin as a starting point. I must specify some additional point y on the surface. Yeah, and likewise, there is a second point in the flat connection, and one may or may not use the same point here. It's charming if there are less marked points in the game, but there are endpoint divergences if you make them equal. So it's up to you whether or not you want to study the coincident limit for p against y or not. So once more, using definition of a path-ordered exponential, this is a huge power series in the generators ai and bi. So again, it starts with terms like that. And now there is a polylogarithm for each ai. But this is just the very beginning. Form a word of arbitrary length. And here,
Beginning of what?
yeah, beginning of an infinite power series. I forgot which informal word I was using half a minute ago.
You won't give us the full power series.
We don't have time for it.
Just a few terms.
Infinite, yeah, there's infinity of powers of j, and j itself has infinite number of letters baked in, since that psi generating series is not terminating.
And T and P are related to X and Y.
Okay, so this j is a one form in t, so t is the integration variable. Or starting from the quadratic piece in j, we have a double integral over t1 and t2. That, for instance. Okay, and let's say the reason that I wanted to expand explicitly up to here is that it takes a while until you actually see a dependence on this additional marked point. The reason is that in this psi object, you need to go up to the subleading order to see the second point at all. So right here, the words of length 2 is the first time where this point p enters at all. But nevertheless, it's certainly present in an infinite number of terms. And to close things off smoothly, let me give a more formal prescription of saying that for all words in these generators, and then there is a polylogarithm for all these coefficients of these words, which depends on the endpoints of the integration path, and this additional marked point where the connection has a simple pole. Okay, from the fact that the chairman is standing already, I will resist in going through an example. If you give me another 2 minutes, I make a comment on Fey identities.
Absolutely.
Okay, thank you.
That was too easy.
Okay. Good. So clearly, this path-ordered exponential per se is a safe and sound story. It gives you a homotopy-invariant integral at each word in A's and B's. But perhaps you're in a scenario where you want to integrate something more complicated. So for instance, you may again face a situation where some of the F tensors are coincident. So for cases like such, we needed Fay identity at genus 1. And in an ongoing project with Eric Doka, we are looking at how to deal with in the higher genus case. So the higher genus analogs of Fay identities. So here is the higher genus version of what I was comparing before with partial fraction. So these two index F's have a simple pole accompanied by a Kronecker delta. So hence, don't pay too much attention to the index structure. And yeah, you can get rid of this term, which is unpleasant to integrate, because there's repeated appearance of x. If you have the plan to integrate over x, then you're in trouble, but you can eliminate this double appearance of x at the cost of terms, 5 on the right-hand side, which have, at most, a single x-dependent factor, and which are in much better shape to be integrated, well, with the definition of these higher genus polylogs popping out of the path-ordered exponential. Yeah, and to check that this is true, just differentiate with respect to the a bar, x bar, and b bar variables. Check that the difference is holomorphic in all variables, so it must be constant. But in fact, both sides integrate to 0 over, say, a. Do a surface integral in a or b, and you will find that it's consistent. So there's no zero mode splitting into the soup. So more generally, we have by now worked out the all-order version of these Fay identities with a proof in 2 steps. Show that both sides have the same anti-holomorphic differential equations, and show that both sides integrate to 0. And that removes all kinds of obstructions to integrate over points on higher genus Riemann surfaces with this definition here. And as such, these Fay identities are an important step or a necessary condition towards a function space that is closed under taking primitives. At least if you want to have an algorithm that pinpoints the primitive with respect to Z integration for you. Good. Yeah, there are a lot of further directions which perhaps we can chat about in private.